first part of this video is going to be boring. It's just, that's okay. If you are watching this as a video, feel free to fast forward until you see more going on. Light blue is really light. So just looking at the graph, assuming it continues down this way, this has 3 turning points in it, so it better be a 4th degree polynomial at least. We tend to want to use the least degree possible. So, but just looking at how many turns there it has, it's got to be at least 4th degree, so we're going to go for a 4th degree. We only have 2 apparent roots, but both of those roots we deflect. Was that what you said yesterday, Aaron? Yeah, they deflect off, or I was saying bounce off our axis. So both of these should be a multiplicity of at least 2. We could say, hey, maybe it's a multiplicity of 4. If it was a multiplicity of 4, I would expect it to go through a little flatter than that, but it's certainly possible. But we want to use, again, the least degree that we can. So those both have at least a multiplicity of 2, so we're going to call them a multiplicity of 2. Also, just the fact that it faces downward tells us our lead coefficient is at least negative. So we at least have a negative lead coefficient. And there's some multiplicity in our zeros. So looking at the graph before we do much else, those are kind of three things that we should ideally see. So then to build our polynomial, we know the 0 or the root or x-intercept at 2 means we have to have a factor of x minus 2 squared because of the multiplicity, because of the bouncing off the axis. X plus 4 because of the negative 4, and again squared because it bounces off that axis, so it has to have an even multiplicity. The easiest thing to overlook, unfortunately, does tend to be this A. That A is going to stand for whatever our lead coefficient ends up being. That A is going to distribute through the polynomial, giving it that kind of the right kind of stretch to it, so that it will go through the points that the particular points that we need off of the axis. So to figure out that A, we need to have at least one point that is not on the axis. And the only point that's real apparent to use here is this point, this y-intercept. We don't have to use the y-intercept to do this. It is especially nice to use a y-intercept. So if your y-intercept is like in between values and we're not sure what it is, but there was some other value, like say this was, you know, clearly 4, -2. It's not. Let's say it was clearly 4, -4. So say we had enough of a grid to know that this point was 4, -4. Then we could use that point to find our A value. So we want to grab the point off the x-axis that we're the most sure about and use it to calculate that A. So this point at 0, -1 essentially has to happen. That means our function evaluated at 0 had better equal -1. So what's our function evaluated at 0? We could multiply all this out first. Our answer should certainly have this multiplied all the way out, but often it's easier to plug it in this form, so I'm just going to do that. If we plugged in a 0, we'd have A times 0 minus 2 squared times 0 plus 4 squared, and that function at 0 is supposed to equal -1. That will allow us to solve for that A that we need to know what this thing's lead coefficient is going to be. So A times 4 times 16 equals -1. So A times 64 is -1. So A is -1/64. And you might notice in comparison to some of our other polynomials, this one is very flat. It's kind of very, you know, squishy that way. And that's because that lead coefficient is so small, or why that lead coefficient is so small. So our full polynomial is going to look like -1/64 times our x minus 2 squared times x plus 4 squared. Now, in a very technical sense, if we stopped now and said, that's our polynomial, that is technically a polynomial. It's not in a nice, you know, not in a standard form of our polynomial. But I stopped myself from saying a nice form because oftentimes the factored form is a nice form. But for questions like this, if you're asked to build a polynomial, I would like to have that polynomial multiplied out in standard form. So I'm going to ask you guys to do that. Mostly because if you are kind of going, oh, I don't want to do that, it's probably because you need practice doing that. So it's good for us. So what, x squared minus 4x plus 4 times.
I don't want to do that because that ugly lead coefficient.
Now the lead coefficient is the exception. I'm not going to distribute that lead coefficient in, but I do want to multiply everything else out. And even if you had to multiply that lead coefficient in, do it last. Do it after you do all the all the other stuff. Now we could do that double distribution like I showed you guys the first time, or we could write this in the area model like we did last time. You guys have any preference on how you'd like to see that all multiplied together? I gotta pick which one I want.
The area model.
All right. Glad you said something because I was about to use the other one. Plus 4 and x squared plus 8x plus 16, and then you don't necessarily need the lines, but I think it helps stay organized. Anything you can do to stay more organized during these kinds of steps is helpful. So then it's just like a multiplication table. So x to the 4th minus 4x to the 3rd plus 4x squared. 8x to the 3rd minus 32x squared plus, I said 32, sorry, plus 32x, and then 16x squared minus 64x plus 64. Now, if you've done it properly and you had each term, like if this was just an x squared plus 4, then everything doesn't line up. So it's often handy to put it in that as zeros, like you do in synthetic division, to make sure things line up. But if you had all your terms, each of these diagonals should all be the same like term. So we just get to add up along those diagonals. So we get the negative 1/64th. And then x to the 4th plus 4x to the 3rd. Oh, was that negative 16 plus 4, so minus 12x squared minus 32x plus 64. Now, distributing that negative 1/64th at this point wouldn't be that bad. We'd have what, negative 1/64th x to the 4th plus, or I'm sorry, minus 1 over 16 x to the 3rd plus, oh, that one's a little more irritating, 3/16 x squared plus 1/2 plus 1. Sorry, minus 1. So it wouldn't be too bad. But if it's a fraction like that, leave it out. I'd rather have the fraction out there than in there.
I have a question as well.
Shoot.
Would multiplying that whole thing by 64, could you put it as distribute the negative 1 across and put the whole thing over 64 as well?
You could. But if you were trying to write the polynomial in standard form,
Yeah.
You'd want that 64 in each term.
Gotcha.
If your goal was standard form. But yeah, you could distribute the negative, put the whole thing over 64. That certainly would also be true, and keep the 64 from giving you all those nasty coefficients as well.
Well, because it doesn't say in this question, doesn't say in standard form. So
no, it doesn't. And that's why I said we could technically stop here. But even if it doesn't say, what form to put it in, I'd like you to at least multiply this together for, your own practice and your own, just because it's a good, polite thing to do. If you're asked for a polynomial, give it in a polynomial form.
So now my question on this one, right? So it says first write the equation for the polynomial and then write your answer in factored form. So for this one, we have to give the polynomial and the factored version as well.
Which one?
For the first one, right? So the question is write an equation for the polynomial. So you write out the polynomial. Right. And then you use the factored form to find the polynomial. So technically both of those would be your answer, right?
Yeah. And it's actually is saying here, write your answer in factored form. So this one's actually asking for this form. You know?
So we don't actually have to figure out what the polynomial is as long as we have the factored form.
Right. But it's good practice. That's all I'm saying. That's all I'm saying. And it gives us a chance to get exposure to other techniques like that area model. Justin, did that work for you?
Oh yeah, I just last time you did it, I think I was doing something else or something like, so I didn't see you explain it.
Fair. It is it's one of those things that some people have seen and they use it a lot. Some people will say they've never seen that before, but it's cool. So it's something I like to make sure you guys see before you go off on your careers.
I mean, the only other option would be to do kind of like a FOIL type distribution of one into the other, and then add up all the like terms, correct?
Yeah, and that's that double distribution way of going about it. I'll do the first step for that. You're essentially taking one of these, thinking of this as a solid object, and distributing that object into each of those terms. So you'll get the x squared times the x squared minus 4x plus 4 plus the 8x times x squared minus 4x plus 4 plus the 16 times, where am I? X squared minus 4x plus 4. And then you can do those distributions and add all those together.
Seems like the area model is a little more efficient. I don't know. I could be wrong.
Well, essentially, this is the first row of the area model. That's the second row of the area model, and that's the third row of the area model. Technically, you're doing all the exact same multiplications.
Right.
But, one is in a different compact. It's just really preference, But from a number of multiplications and addings you have to do, it's actually exactly the same. But one kind of keeps it organized for you. It lines everything up. One happens, in line with the work that you're doing. So it's just a preference. And either one's good. Do you guys need some more time to play with these other two, or are you ready to talk about them? Crystal, your answer is yes. Yes to which one of those things? That you want to talk about them?
Okay. I have a question on number 2, but I don't want to go for it before people have solved it. Once you get down to the last, when you're using the quadratic for the last part of it.
Mm-hmm.
So for me, I got 6 plus or minus 10i over 2, right? So because you end up with square root of negative 100.
Mm-hmm.
So once you break that down, it's 10, obviously, and you get 10 times I, which would be your negative 100 square root. How do you distribute the 2 on the bottom? So once you're dividing, right? So obviously 6 divided by 3 is 2.
Mm-hmm.
How's that going to affect the I, though? That's my question.
Let's get to that, and we'll do it.
Okay.
Because I'll show you. So there's a nice way to think about it.
Kind of confused right there.
Yeah, we'll look at that.
So I don't want to divide the I by 2 because that would be weird.
Well, let me just, we'll look at it down there, but just real quick, if you have that 10i divided by 2, 10i divided by 2 is what?
5i?
It's 5i.
I didn't know if that would be okay, though.
Absolutely.
Okay.
So we want to find all the zeros of this. To find all the zeros of it, one of the nice things to do would be to factor it. We could get a list of possible rational zeros from this and compare that to our graph. But is there anything anybody did first to this problem to try to make it nicer?
What about the bag that you had your sand on?
It has nothing to do with sandals.
Hurry up.
Oh, sorry.
Anything anybody did first to this to try to make it a little bit easier?
I divided it by 3.
Absolutely. I always say a good math person is really kind of on the lazy side. They look at something and go, what is the easiest way? What can I do to make this less work for myself? If there's something you can do to simplify it before using the bigger tools, do it. Factor out that 3. Absolutely. Now, even for a rational root theorem, the factors are smaller. So a lot of the choices that we get for those possible fractions have been reduced way down because we pulled the 3 out of the whole thing. So then our b over a's, we even got that lead coefficient of 1, which is ideal. Those b over a's will be 1, 2, 3, and 6 over 1. So just plus or minus 1, 2, 3, and 6. So really shortens that list up real fast. So that's the first thing. Then we start looking at these values. This is only 8 values. We could just start checking them. But glancing at that graph is certainly handy. And the one that stands out, I don't know about you guys, but the one that stands out to me is that -1. Is that fair? So I'm going to grab that -1 and do the synthetic division on this reduced form. That 3 has been pulled out. We're just trying to factor what's left. So again, that keeps our numbers smaller, more under control, and will reduce the amount of simplification we have to do later. So it brings down that 1, -1, -5, 5, 6, -6, 0. So great, the -1 worked. We could check some, see if, hey, if I think that's a 2 or whatnot, we could check those. But we've got a quadratic here, so the remainder or the rest of our problem we can handle for trying to figure out where that quadratic is equal to 0. It sounds like, Andrew, you went right to that quadratic formula.
Not for this one. For this one, I kind of figured it out with the graph. I was talking about the third one.
Oh, you're talking about the third one. Okay.
Yeah. But for this one, I didn't factor out the 3 either at the beginning. I did it a little differently.
And it's perfectly okay not to. It's just that your numbers are going to be bigger.
Yeah.
But I think this is factorable, isn't it?
Yeah, that part is.
To what, -2 and x -3? Which means with the 3 in there, you'd have certainly had a bigger thing here. It would have been what?
You get a 3x minus 3.
Minus 15x plus 18.
Yeah.
That's still factorable. But you're right. One of these then has a 3 in it, and the other, so it's harder to factor.
Yeah. So my final answer on that came out as x plus 1 times x minus 2 times 3x minus 3.
3x minus 3 or 3x minus 9?
Well, after I did the synthetic part of it, it was 3x minus 3 for the last part. Because you would have had, I am minus 9, you're right.
Okay.
I was reading my paper wrong.
Okay. So our factored form, in how I've got set up here, our factored form would be the x plus 1 that we started with, the x minus 2, and the x minus 3. But yeah, if you had left that 3 in there, which would have been extremely reasonable, either that would have been 3x plus 3, that would have been 3x minus 6, or that would have been 3x minus 9.
Yeah.
They all would have been the same. Our zeros are still the x equals -1, 2, and 3.
Okay, so I got my zeros correct, but I'm confused where the -9 is coming from.
Well, if this 3 had been distributed just into here,
Mm-hmm.
that factor would have looked like 3x minus 9.
Got it. Okay.
And if you were left with, if you didn't bring out that 3, you'd have been left with that, right?
Yeah.
and that factors into 3x, x, and then we got to find something that makes this 15. So what makes 18? A couple different things. 9 and a 2 makes 18, right? And that would be 9 and 6 to make the 15. So 9 minus 2. That's going to make the 18, the 15, and the 3. So that's the factored form.
That's how I got there.
Okay.
But even at this stage, going, hey, there's a 3, factor that out, and then at any point when you realize, hey, I can factor out a 3, you're going to make the problem easier.
Yeah, I should have seen that in the beginning. That would have made my life a little simpler.
But I think it's nice, though, that it works out anyway. It's just, you can speed yourself up, have a nicer day. And if you'd have started by saying, hey, that looks like a 2, and started with the 2, you'd have gotten a different polynomial, but it would have factored into the other pieces. So in this one, because they're all nice rational solutions, really any of those choices would have been fine.
Yeah, I have a really hard time sometimes recognizing, like, taking that first step. I just like look at the whole thing as a whole and how to break it down.
Yeah. Well, and that's one of the things that the rational root theorem is good for. The rational root theorem says, okay, focus on these 2 that we can look at. These will come out in the wash later.
Yeah.
Yeah.
Now, another question, since we're here, and this is kind of what this is for.
Mhm.
When I put it into the graph, right, I mean, obviously there's pretty clearly, like, the answers came out the right way, roughly.
Mhm.
Because if you factor out the 3 right away, then it's just x plus 1, x minus 2, x minus 3. And all those zeros are pretty clearly represented on this graph.
Mhm.
So if it's pretty obvious like that, and you can prove it with just a simple, like a couple simple, just each one of these synthetic division things, do you have to write out like all this for credit?
No, as soon as you get to this like stage, we went to not even the quadratic formula. We just factored
Yeah.
it by hand.
Yeah.
But if you wanted to go and say, okay, I think that 2 is also a root, and do the synthetic division with that 2, you'll have a 0.
Yeah.
And what's left, you can then either solve that and you'll get the 3, or go, I'm going to do synthetic division again with a 3, and it will turn out to be a 0. So
Yeah.
you could have done that as well. Absolutely. That won't work when we have either non-real solutions or irrational solutions. But when the
Yeah.
problem is fully factorable, any of the methods are going to work out nice.
Okay. Yeah, the next one's not as pretty.
No, not at all. But what did we do next? Well, what did we do first for the next one?
Minus 34.
Minus 34 to have it set equal to 0. Okay. And then we got a polynomial that's set equal to 0. Oh my gosh, what do we do to solve a polynomial set equal to 0? We try to factor it. Okay. If we're going to try to factor it, we would like to have some possible zeros. So those possible zeros, again, we thank the lead coefficient of 1. The factors of 34 are what, 1, 2, 17, and 34? In some ways, the fact that 34 is not a terribly nice number is good, because it means it doesn't have a lot of factors. If it was a nice thing like 36, I hate seeing 36, because 36 has so many factors. So since that lead coefficient is 1, we just have that 1, 2, 17, and 34. And of course, plus or minus. Now we could start checking them randomly. It's actually not uncommon for people to check the 1s even before making the graph, because the 1s work out so often. So sometimes I'll do that. But looking at the graph, certainly I don't see a 2 or a -2. There doesn't seem to be anything on the negative side. We could go see if it looks like it crosses at 17, 34, or -17 and -34 by looking out on the graph if we wanted to. But God, this +1 stands out so much. And if the +1 works, it will reduce this to an x squared, and then our quadratic skills can take over.
Do the ones work out often because the leading coefficient is 1?
More often when the lead coefficient is 1, absolutely. But even when the lead coefficient's not 1, it's not an uncommon factor to be in things. And it's so easy and fast. So easy and fast to check it that if it works, it can save you some time. For us, I certainly recommend, make the graph, make the list each time, but testing that one real fast, if it looks like it's, like, hey, actually that might work nicely, it's often a nice thing to just check fast because it works so nicely.
Right, because I was thinking that because that's kind of the reason why the last problem became easier when we factored out that 3, because it made that leading coefficient of the polynomial we were trying to break down a 1.
Yeah, and that's always going to be an advantage. Anytime you see a lead coefficient, it's really appropriate to have the reaction of, a lead coefficient. Ooh, I wonder if I can factor it out. Oh, yeah, I can. Or sometimes you can't. And you go, nope, just going to have to deal with it.
Oh, thank you.
And it might not be good life advice, but it is good math advice. If there's something you don't like, try to find a way to avoid it. I don't know if that's good for like family and relatives and stuff, but for math, it surprisingly often is. Except fractions, Andrew, not fractions.
It works great for family.
Good.
Well, there's definitely some people I've factored out in my life.
Yeah.
I am with you on that one.
So let's try that 1 and see what happens. Again, we're being careful to make sure we don't have any zeros. 3, 2, 1 constant, so no zeros. So 1, 1, -6, -6, 34, +34, 0. Yay. Okay, so that 1 isn't an irrational number that's being sneaky. It actually is a 1, so that's one of our factors. Thus, x equals 1 is a solution. We're then left with the x squared minus 6x plus 34. We could certainly, if we wanted to, check, the positive or negative 17 or 34, or look for it on the graph. But frankly, it's probably not going to come up. The larger values don't tend to. And, what's the reasons we have our quadratic skills is so we can have them take over here. So good old x equals 6 plus or minus the square root of, 36 minus 4 times 1 times 34 all over 2. 6 plus or minus. You're saying that was -100?
That's what I got, because -4 times 34
is 100. Okay, I believe that. Anybody else believe that? Yep, okay, good. So x equals 2 plus or minus 10i over 2. And you were asking about this division. I like to remind people that there is no such thing as division. There is only multiplication.
Yeah.
So this is really 1/2 times 6 plus or minus 10i. So you're really distributing that 1/2 to each term.
Gotcha. I just want to make sure, I felt like that was what I was supposed to do, but the I kind of threw me off.
Oh yeah, eyes are weird, and they always make people kind of doubt what they're looking at because eyes behave weirdly. But the nice thing is, in a lot of ways, eyes they don't make any of our mechanics that normally work. eyes never make those mechanics not work.
Yeah.
There are extra things eyes do, but there's nothing that a variable does that an eye won't do.
It doesn't restrict anything.
Right. It only adds power to us. You know, the fact that if we square it, it turns into a -1. That's its big trick. Other than that, you treat it as if it was just an X or an A or a B or anything else.
Yeah, I remember that trick from 95.
Yeah. So those are our non-real solutions. We were asked to give all our complex solutions. Do remember 1 is a complex number. It's just 1 with no imaginary component. And 3 plus or minus 5i are the other 2. I want to, well, before I say a little something else, is there any questions on that problem or any of these? They go fairly well. Keep getting the practice on them so they're, faster and smoother and whatnot. But if it's going good, that's excellent. But a little note about complex numbers, imaginary numbers, and real numbers. So the number, say, even just a number like 5. 5 is a natural number. It's one of the counting numbers. 5 is an integer. It's a whole number. It's a natural number. It's a rational number because we can write it as 5 over 1. And it's real. So there's a lot of classifications for 5. 5 is also a complex number. Complex numbers are anything that can be written in the form a plus bi, where I is that square root of -1. And we can write 5 that way. It's 5 plus 0i. So it is a complex number. It's just 1 with a 0 imaginary coefficient. So every number you've ever dealt with, really, for the most part, depending on what you've done with your life, is a complex number. It's just a complex number with no imaginary piece on it. So if we look at a number like, say, 3 plus 2i, 3 plus 2i is not a whole number. It's not an integer. It's not a rational number. It's not an irrational number. It's not a real number. The only thing we can call this is complex. It has a real component of 3. It has an imaginary component of 2. It is a fully robust complex number. There's no other classification for it. A number like 7i, and again, all of these are a single number. This is a single number 5. This is the single number 3 plus 2i. That's always weird. This is the single number 7i. Again, that is not a whole number. It's not rational. It's not irrational. It's not real. We can call it imaginary because it has no real component. As a complex number, this would, just like this was 5 plus 0i, this is 0 plus 7i. So it has no real component. So while it's still a complex number, again, everything's a complex number, because it only has an imaginary component that's not equal to 0, we can call that number an imaginary number. So be careful. This is not an imaginary number. I know even some fairly experienced instructors that will casually call this an imaginary number just because they're kind of getting sloppy. It's not. It is a complex number. To be imaginary, you have to be fully imaginary. You can't have a real component. Just like to be real, you have to have no imaginary component. If you have a bit of both, then you're not real because you're not fully real. You're not imaginary because you're not fully imaginary. You're just complex. So careful about that word imaginary. Sometimes people use it in overly broad sense. Does that make sense? Cool. All right. All your stuff up to, I think, 4.5 is due Monday. 4.5 is these problems with the complex pieces in them. So make sure you finish that up. We will do rational functions and inequalities and such, and maybe power functions. We may or may not do the section on power functions next week. And if between now and then anything comes up, let me know. Have a wonderful day.
Sounds good. Have a good day.